So last week, hopefully, I made the case that either by submitting all of our information to a central decision maker or by talking with each other, we can make an efficient allocation of power. So the cheapest suppliers will produce, the consumers who want to consume most will consume, and that is the efficient solution. So the question now becomes how we can set up a set of rules so that we can exchange the goods if we didn't do it through a central supplier. And there's a range of options here. So the simplest thing we could do is just have a purely bilateral market where we go out and seek a counterparty, so someone who wants to buy what we're selling or someone who sells what we want to buy. There's a more organized setup where there's a more organized setup where we can post our offering online. So one of the thoughts I had for your auction exercise was in fact to not even set up an auction. One idea I had was to have you talk with each other and try and trade the power that was in the power that you had to offer as a supplier, have to consume as a consumer. I'm assuming you all got emails about whether you're suppliers or consumers and so on. And if I had set it up that way, one option for you would have been to set up like maybe a Facebook page and say, post on this Facebook page, I have this much power and I'm willing to sell it at this price and wait for someone to contact you through Facebook. And that's a way of trade which is still bilateral. You're still looking for someone else to trade with, but it's facilitated by being able to communicate through the internet. That's why bulletin markets are currently very popular. Then there are more organized setups, for example, the way we sell and buy houses, where we have a broker, and the broker is a person who makes connections between us, the buyers of a house, and the sellers of the house, and they take in their pocket a commission. So that is a more centralized setup, where the central piece of the market is the broker, and then even more centralized setups is what we're doing basically with our auction this week. Is we have an exchange where the rules of the game are simple. We described them last week. You know how the auction is going to unfold. You know what information you need to submit, and you know the rules for setting the price. You don't know what the other people in the market will do, but you know what the rules are, and they are fairly simple. We have this supply curve that is increasing, the demand curve that's decreasing, and when they intersect, that's the price at which the power is sold. And then we have more complicated, and that's, for example, how the New York Stock Exchange functions. So it's a centralized auction. It all goes through a central auctioneer, but the rules of the game are fairly simple. Now, for electricity markets, you have an even more complicated setup, which are pools, where there are multiple products being traded at the moment in the exercise that was assigned to you. The only thing you need to trade is energy, either buy it or sell it. But you will see later in the course that a generator can provide more than just energy. They can provide also backup services to the network. I think Rafael brought that up in last week's lecture. You have then more complicated auctions where you're still submitting a bunch of information about yourself, but now we're trading multiple products, and there are multiple prices for these multiple products. And the way these prices are determined, again, the rules are stated to you, but they're more complicated than just taking a supply curve, a demand curve, and finding their intersection. And that's called a pool. So we'll see that when the unit commitment problem comes up. Now, what's the benefit of being able to talk with each other, so engaging in bilateral trade versus doing something more centralized? Well, when we are looking for someone to trade with, there's more flexibility. I mean, there is no set of rules that we have to follow. We can just go out in the world and find someone that is willing to take the price we have to offer. On the other hand, if you think about it, if last week's exercise I had set it up with you having to look for someone individually, you would not have known a price, a public price, in the end of the day. You would have found someone to trade with. Whereas in the auction game that we're playing, you will know the price after the exercise is done. So tomorrow when you submit your bids, we will clear the market. We will tell you what the price is because we need to tell you what the price is so you get paid. So you have in an exchange, which is a more centralized setup, you have a public price that is announced. Whereas if we trade bilaterally, we can whisper what opportunities one came up with, but we will never know what the price of the good is. And then it's not necessary to even set up a market to only follow one of these models. You can have a mixture of these things taking place. So you can have markets that allow bilateral trading and auctions at the same time. Now, the problem with economic dispatch is you cannot run bilateral trades in economic dispatch because there's not enough time. And this exercise that was given to you happens in power systems every 5 minutes, every day, because we need to be balancing supply and demand continuously. So imagine if you had for the coming week to not just solve this exercise for tomorrow, but you had to solve it for every 5 minutes. And imagine you had to do that by having to look out for trading partners. It could be done, perhaps, but it's much more difficult and much more slow than just sending information to an auctioneer, which is the way that things are done currently. And then the other problem, and you know, one of the disadvantages of doing this bilaterally is I'm a supplier, maybe I do find a consumer, I quote a very high price, much higher than my marginal cost. I do find a consumer who's willing to buy, but then how do I know I can trust him? So I give him the good, but it's possible that the counterparty never pays me back. Whereas in an exchange, once you submit your bid, the exchange becomes a counterparty. That the exchange is the person who will make sure that you get paid for supplying the good. So there are disadvantages. There are certain disadvantages with bilateral trade that make it impossible to use for trading electricity in real time. And then the other disadvantage is that in an electric power system, so when we're trading potatoes, for example, I walk up to you, I tell you, this is my price, you want to take it? If you say yes, and we agree on a certain quantity of potatoes, I give you 5 potatoes, and it's 5, and I'm the one who gets to give them to you, and that's how the trade is done. But in an electric power system, even if you say, yes, I'll buy your power, you can always turn your switch on for longer and use more power. The problem with electricity as a commodity is that it's not potatoes that we can physically take and give to someone else. It's an electric network, which is like a pool where the suppliers throw in the power, the consumers draw the power out, and the only thing you can do is monitor what each person is doing, but you can't control how much they are consuming. So you can only observe the quantities that are supplied and consumed after the fact. So a consumer can consume more than they agreed to in the trade, and the supplier can supply less than they promised in the trade. And the only thing you can do is observe it, and then after the fact go to billing, which is again different from a bilateral trading setup. Okay, and this is briefly describing the auction that was assigned to you for the game in the homework. So the rules are very simple. We have generators and consumers, and the generators submit price quantity pairs For generators, a supply bid is interpreted as follows. If my first price quantity pair is here, so for example, 5 megawatts at $10 or euro per megawatt hour, this means that the first 5 megawatts of my supply, I'm willing to offer them at $5. And then I have another 10 megawatts that I'm willing to supply at a slightly higher price. So this is another price quantity pair, which means that I move to the right of 5 by another 10. So the total quantity is 15. So this segment of 10 more megawatts, I want to supply at a higher price. And you submit 3 of these price quantity pairs. The way we, the auctioneer, understand this is in the way I just described to you. Similarly, a consumer submits its own price quantity pairs, and it's saying that, for example, the first 3 megawatts, I'm willing to consume them at 80 euros per megawatt hour. So I'm willing to pay 80 euros per megawatt hour for the first 3. So what we're going to do as the auctioneer is take a line here and put your block over here. The next 7 or like say 8 megawatts, I'm willing to consume at 60 euros per megawatt hour. So we take another 8, we move up to 11 here, and so on. So what we're going to do is collect all these bids from you, stack them for the consumers in decreasing order, for the suppliers in increasing order, and we will find where these 2 curves intersect. We won't tell any of you what the other person did after the exercise is done. All we will tell you is the price, the point where these curves intersected. And that price, for you, for those of you who are, so assuming these 2 curves intersect, for example, if there were a third bid that is over here, these supply curves and demand curves would intersect at this level of price over here. So we would announce 15 as the market clearing price. That price is the price that all of you get paid for supplying. Well, those of you that made an offer at 15 or less. Why? Because when you gave me your price quantity pair, you said, I'm willing to supply at 10. Well, if you're willing to supply at 10, you're also, if you get paid 15, you're certainly willing to supply 5 megawatts. Similarly, the most highest valuation load here said, I'm willing to consume these 3 megawatts at 80. Well, if I sell at 15, you're definitely willing to consume 3 megawatts. So all we're going to tell you after we take all of your bids is a price. And that price will be used for computing your payoff. For those of you who will consume, the payoff will be the market clearing price, let's call it lambda, which in this example happens to be 15. So for suppliers, your payoff will be the market clearing price times the quantity you are told to supply minus your fuel cost. How much do you need to supply? Well, if you are, yes?
Is this lambda related to the constraint or?
Yes, it is. In the economic dispatch problem, it is the dual multiplier of the power balance constraint.
The equality.
Come again?
It's the equality constraint.
Of the equality constraint, exactly. Provided that you bid truthfully. You don't have to say the truth here. Okay, you can see how not saying the truth could help you. If you quote if your supplier you quote a price that is higher than your true cost, you can push the price higher. So you could benefit from deviating from the truth. So this lambda is indeed the dual multiplier of the equality constraint of the economic dispatch problem, provided you all say the truth. But if you deviate from the truth, it's just intersection of these two curves. Is that clear? Yes.
What happens if there is no intersection?
Okay. There. So, can you give me an example of a situation?
For example, if
the third block was larger.
yeah,
The third block here
continues to the right.
Okay. So if we have a situation like this, we will need to announce a price. Okay, remember again, what the auctioneer is doing is obeying these rules that were announced to you. So the understanding is that this guy who did this block over here is indifferent whether he consumes or not at that price. So let's say this price is how much? Let's say it's 45, for example. So what I'm going to do here is quote a price of 45 and take part of his bid. If I quote a price of 45, and all of the suppliers are willing to supply at that price because they offer that less than that. So I can take their full amount of power. But this guy, I'm only going to take this part of his offering because he's indifferent whether he consumes or not. So I quote a price of 45, and by following the rules of the auction, I tell him, you will pay 45, but I will only take this portion. You will only consume this amount of power. Okay, so that way I use the price to clear the market following the rules of the auction. Of course, anyone who's to his left is willing to consume at 45 because they offered to buy at higher than that. Now, there's this terminology of suppliers who are below the market clearing price are in the money because they get to trade. In the money for a supplier means I offered something less than or equal to the market clearing price. And similarly, consumers who are higher to the left than the market clearing price are also in the money. They get to also trade, they get to consume. And then anyone who's to the right, consumers and suppliers, are out of the money because they were too expensive as suppliers or too cheap as consumers. Is that clear? Yeah.
And the third guy is in and out the money?
This guy here, this part of his bid is in the money, and this part is out. Okay. Okay. So now, what's the good thing about this setup is this is an auction. This is a way for us to organize an exchange of power between us. But it's also highly compatible with how the control room runs. So what changed from the days of regulation where the whole supply chain was controlled by a single company from top to bottom versus this situation is that now what we're doing is we are also submitting bids. They go to the control room, but the control room solves the economic dispatch problem and takes the lambda multiplier as the market clearing price that it will send out. And other than that, it does everything the way it used to. So by introducing a market around real-time electricity trade, nothing changed. The only thing that, from the point of view of the control room, nothing changed. They just ask for people to bid in. They run the economic dispatch. The difference being that when they used to run it in the old days, they owned the generators and they had the load, so they knew what the generator cost and the load demand was. These days, they just ask people for this information, and other than that, the control of the power system runs as it used to. And that's very appealing for, you know, when you're making a structural change in an industry, you don't want to introduce something that will destroy the way that the system was used to be operated, because companies are organized around this structure. Engineers, you know, spend years in the control room learning how to run the grid. If you introduce a market around the grid and completely change the way the grid is controlled, you are likely to mess things up. So it's very appealing to introduce a uniform price auction around the economic dispatch problem. The reason it's called a uniform price auction is because we all get to buy or sell at a single price. And there are other options you can set. And we'll see an example of a different one where there is not a uniform price. So hopefully this example here just reiterates what I drew over here. So here we have a bunch of supply bids, which are the red ones, a bunch of demand bids, which are the blue. The market clearing price is 28 in this example, and it's straightforward to compute the obligations and the payments. By obligation, I mean, for example, the supplier right here that is in the money, the red block, the first one, has an obligation to offer 30 megawatts. They bid 12, but they get paid 28. This last block over here has no obligation. They don't get paid anything, but they don't need to supply anything. These are kind of squeezed over here, but in the textbook it's more stretched. So this example is analyzed in detail in the textbook, but hopefully what we did over here clarifies things. Now, this is a specific choice of auction. It's not the only way we could have organized trade between us. And the choice of a uniform price auction for electricity is not coincidence. There is a good reason that market designers have chosen this specific way to clear electricity markets. And one way to justify it is the following. I will say now, and prove and show to you in the next slide, that this very closely resembles Vickrey's second price auction. And now I will tell you what Vickrey's second price auction is. Suppose we are selling a, forget about electricity for a moment. Let's think we're all in an auction in Sotheby's in London, and we are buying a Picasso painting. So the item to be sold is a Picasso painting. And we all submit a bid for buying the painting. So in the setup of the painting, we give the painting to the bidder who made the highest offer to pay for that painting. But the rule of the auction is that that person who's the highest bidder gets to pay the price quoted by the second highest bidder. Now, why do we do that? If you think about it, the reason to do that is to make everybody say the truth about how much they want the painting. If I'm think from your individual point of view, is there any benefit from saying a number that is higher or lower from how much you would like the painting? There's none. If by quoting a lower price, you're hoping to push the price down, and you're not going to push it down, because either way, you are going to pay the second highest bidder's price. It's not your price that's going to set the price of, at which you will buy the painting. Whereas by quoting a lower price, you might end up losing the painting if the price lands between your quote and your true valuation. So if, for example, I want that painting, if I'm willing to pay for that painting 1,000 euro, and I quote 900 euro, with the hope of buying it at 900 euro just because I pushed the price down. Well, on the one hand, it's not my price. If I end up being the highest, the person with the highest valuation for the painting, it's not my choice of bid that will set the price. And if the price ends up being 950, then I'm really upset because I wanted it at 950. I was willing to pay 1,000. And I ended up undermining myself by bidding 900. So there's no benefit in pushing my price bid down. I'm just decreasing my chances of winning the auction, and I don't have any influence on the price. So it's a dominated strategy to bid 1,000 or more. Now, is there any point of bidding 1,100? Again, why would you do that? The reason you would do that is because you want to increase your likelihood of being selected to buy the painting. But if by bidding 1,100 you end up buying it at 1,050, you're basically not that happy after all because you just wanted to buy 1,000. So there's also no incentive to bid above your truthful valuation because you better not be selected if you bid above your truthful. You might want to do it because you want to increase your chances of winning the auction. But if you win the auction, you're actually thinking back, you really didn't want it that much. So, bottom line, second price auction gives us the incentive to bid exactly our valuation. Now, flip the situation around and now think of supplying something at a certain cost. The second price auction gives you the incentive to truthfully bid your supply cost. Not more, not less. And if you think about how this uniform price auction for electricity trading was set up, it's kind of like that. Typically in bar systems we have a demand side that is fixed. These bids, the valuation bids do exist, but they are very steep, which means that you can more or less think of demand as fixed. And we have these bidders that are bidding and increasing supply. The only difference between this and Vickrey's second price auction is that bidder K plus 1 who sets the price also gets a bit of a reward, whereas in Vickrey's second price auction, bidder K plus 1 who is the losing bidder, they do set the price, but they don't get this little reward here, whereas in an electricity price auction, this little segment of that supplier is in the money. So it's almost like a Vickrey second price auction, but not quite. From the point of view of bidder K, it is exactly like a second price auction because it's the losing bidder's supply bid that will set the price. So that's hopefully the analogy is clear. I should not have used an example of an auction where we're selling a painting instead of supplying something, but hopefully the analogy is clear. Bottom line is that the rules of the game are set up to replicate Vickrey's second price auction, and in the absence of market power, so big players who control most of the supply in the network, this game gives us the rules to say the truth to the system operator about how much we need power if we are consumers or how much it costs power if we are suppliers. Now there has been a discussion, and this is one slide where I mentioned this in the beginning of the course. We do go through some economic concepts, but just for the sake of giving you an understanding of how the industry is debating things rather than doing a thorough economic analysis of auction theory, what I want to give you in this slide is a view of the debate that has been around in the power industry about should it be a uniform price auction or other auctions. And one alternative that was proposed was pay-as-bid pricing, where the rules of the game are that you will get paid for each block what you, as a supplier, what you bid for your cost. So the way we define this, the obligations is the same. We bid price quantity pairs, we find who's in the money and who's out. The difference, however, is that those who are in the money, if they are suppliers, they get paid what they declared as their cost. If they are consumers, they get paid what they declared as their valuation. And if you think about this set of rules, it's very different now from a uniform price auction. Because in pay-as-bid pricing, I do have an incentive to say, to not say the truth. Because the price I get paid is only depends on my bid. So a pay-as-bid pricing auction actually gives us incentives to lie about our valuation if consumers, our cost if flows. Why did people propose this? Well, there was behavior that was observed in some markets, for example in Texas, with uniform price auctions, where you had suppliers that every day were bidding hockey sticks. So what they were doing is sending out, and this could be an interesting idea for your game. So they were, suppose you're restricted to 3 bids. And you bid this. Why would you do this? And this is called a hockey stick because it looks like a hockey stick. Why would you do this in a uniform price auction? Any ideas? Yeah.
If there is an intersection with the highest, the price would be the highest price. Or
Yeah.
Then we have a great benefit.
A huge benefit. It goes to everyone. The huge price goes to everyone. If this little slice is the one that happens to set the price, it sends the price out of the roof. More often than not, it's going to be out of the money. So more often than not, it's going to land to the far right of the supply curve. But there will be days when demand will be very high, so all of the demand bids will be all to the right as well. So there will be a few days when this spike will be in the money. If it's in the money, it sets the price. It's a huge price. And the days that it's not in the money, big deal. You just so you can make this slice really thin and lose a megawatt every day out of, if you're say supplying 1,000. So maybe every day you end up losing 1% of your quantity supply, but the one day that you hit jackpot and you end up setting the price with the spike, you are a very happy person. Now, this was observed in Texas, and the regulators stepped in and forbid it. So that's one of the criticisms about uniform price auctions. How would the pay-as-bid auction be different? Would you have the incentive to do something like this in a pay-as-bid? The key difference in a pay-as-bid auction is that in a uniform price auction, if this is a bid that sets the price, all of the bids that are in the money get paid that same price. In a pay-as-bid auction, it's only this slice that, even if it happens to be the money, gets paid this price. So the profits are much fewer. So your incentive to do hockey stick bidding is much less. So that's one of the criticisms that people had that motivated them to propose pay-as-bid pricing. But the counter-argument is, and then there's another criticism, that why should this person here, who only has a fuel cost of 5 euro per megawatt hour, why should they get paid for 15? It seems like it's unfair, it's unreasonably high. But we will see later in the course that there's very good reason to pay their bidders that are in the money above their fuel costs. The reason being that they also have constant investment costs that they need to cover. So if they're always paying just their fuel costs, well, who's going to pay for the constant costs of building the plant, for example? So there are reasons to actually clear suppliers in the money with the price above their fuel cost. And then in the counterattack, so when people attacked uniform pricing, there was a debate in the counter-arguments against pay-as-bid pricing. So for those who are proposing pay-as-bid pricing, one of the arguments was that on the one hand, you're giving me incentives to lie about my cost. On the other hand, why do each of us get a different price for selling the same good, which is power? So discriminatory pricing, which is the first bullet here, means that different suppliers get different prices, and that's not a good feature of setting up a market. For example, in the European Commission explicitly states that the European market has to be set up in order to be non-discriminatory. Everyone gets paid the same price for supplying the same good. And then there's this last argument that if you set up a pay-as-bid pricing option and people end up bidding truthfully, they will become extinct. Because if they are in the money, they will get their fuel costs covered, but they will not get their investment costs covered. So it's not a profitable investment, and you will end up having low fuel cost, high marginal, high investment cost units dying out, whereas a network needs them. That's all there is about auctions. So hopefully this information will help you reflect about what you need to do with your bids for the exercise. And any outstanding questions, or should we move? Okay. Okay. The next topic we will discuss will be the economic dispatch problem with power flow constraints. And we will see what power flow constraints are in detail in the next, after the break. Before jumping into power flow constraints, I want to talk very briefly about graph Laplacians, because they will help us understand a bit of the mathematics behind power flow constraints. So this is part of the math background chapter in the notes. I will briefly define a graph Laplacian, go through two of its properties that are helpful to remember, and then after the break we'll jump into power flow constraints. So moving from auction theory to graphs, the definition of given a graph with a set of nodes and edges, we define an incidence matrix, which is a matrix defined over the set of the rows of the matrix are over the set of nodes of the matrix. The columns of the matrix are the set of nodes in the graph, and we have one entry if row I, column J corresponds to an edge of the graph, and the zero entry otherwise. And the degree matrix is just a diagonal matrix that assigns in each element of the diagonal the number of edges that are adjacent to that node. So then the Laplacian of a graph is the difference of these two matrices. And here's a concrete example. So we have a three-node graph. The incidence matrix A puts a 1 at, well, it assigns all the diagonal elements are 0 by the definition of the incidence matrix. And for row 1, column 2, we go and stare at node 1 and node 2. We check if there is an edge connecting them. We assign a 1 if there is, a 0 otherwise. Here you see that all the off-diagonal elements have 1s because this is a complete graph. And then the degree matrix is just putting in each of the diagonal elements the number of adjacent nodes. For element 1.1, we look at node 1, we check how many edges are coming into node 1, we observe 2, so we put the number 2 here, and the Laplacian is just the difference of D and A. So if you think about it, the diagonals of the Laplacian just have the number of nodes adjacent to that specific node, and then in the off-diagonal entries we have -1s whenever the other node is connected to the node in question. So one thing to observe about this matrix is that it is positive semi-definite. What is the definition of a positive semi-definite matrix? Is you give me any vector you like in Rn that is non-zero. If I take the left and right products with respect to the matrix A, and this product is greater than or equal to 0, then that is a positive semi-definite matrix. So how come the Laplacian matrix is positive semi-definite? If you look at the way the matrix is set up, so what we're doing is, let's think of the ith entry of the vector LF. So what happens when we hit the Laplacian with any vector f? Let's look at the ith entry. There will be one guy sitting in the middle of the diagonal here, who will, which will just be the degree of the node I. And that element will hit element Fi here by a constant which, say this constant is alpha. If that alpha is the constant sitting here, then I know that a -1 will occur in this row alpha times, just by the way the Laplacian matrix is defined. Which elements will have a -1? Well, they will have a column number that corresponds to nodes j in the graph to which node I is adjacent. So then what we get is an alpha times Fi minus sum over I comma j, provided that I and j are an edge in this graph, Fj. And I can just split this by assigning one Fi to each of the j's. So this is just equal to okay. And that's what I am writing here. So the ith element of LF is just sum over j, provided that I and j are an edge. This graph of Fi minus Fj. So then I get this column vector. I hit it from the left by the same vector F1 through Fn. And what I get is this summation here. So I'm summing over Fi times the ith entry of LF. And I want to say that each of these pairs appears exactly twice. So let's think, for example, of what happens with F1. And any node j that F1 is connected to, well, that F1 is going to show up once as F1 times F1 minus Fj But then there will also be an fj here that will hit fj minus f1 from the right-hand side vector. So what's happening when we're taking this inner product is that we are having each component fi hitting fi minus fj, provided there is an edge between I and j. But then when we are also considering that fj, it will eventually meet an fj minus fi, because that is also going to necessarily show up in this vector. So what then happens is that basically we can take the summation over the edges out, and we're left with these two summands here. So we factor out the fi minus fj, and what's left is on the left hand side the fi, on the right hand side the minus fj. So we just get a sum over all edges of fi minus fj squared. Now this is non-negative, so this proves that the Laplacian is positive, semi-definite. And again, the rationale here is that if we are able to find an f1 that multiplies f1 minus fj, then we will be able down the line in the fj entry from the left-hand side find the f1 again. So that's the structure here. So an example for the three-node graph that we saw earlier is this is the LF matrix. So we get in the first row f1 minus fj, where j corresponds to any node that node 1 is connected to. So node 1 was connected to node 2, and node 1 was connected to node 3. So in the first entry here, we get the difference of f1 minus f of whatever node 1 is connected to. So then when we're left multiplying by f, we get one product of f1 with f1 minus f2. But if we go down the line, sure enough, we discover f2 multiplying f2 minus f1. Since 1 and 2 are connected, this product will show up in the first multiplication of the first entry f1 with this stuff here, but it will also show up in the multiplication of f2 with this stuff here. So then if we go through the algebra, we get the sum of the squares of fi minus fj, where I and j are edges. Now, okay. So one way to interpret what's going on here is that the if f is assigning a weight to each node I and j, basically what this f transpose LF is doing is taking the variance of this vector f over the entire graph, which is a non-negative quantity, which is basically establishing the positive semi-definiteness of the Laplacian. Now, the important thing that we will end up using is that the Laplacian is the number of zero eigenvalues in the Laplacian is equal to the number of connected components in the graph. So if, for example, I have a graph like such, and I form the Laplacian of this graph, the number of zero eigenvalues of this Laplacian matrix is 2. And this will be useful for us later in the optimal power flow problem, because if the graph is connected, which we assume a power system is, we know that the Laplacian of the graph of the connected power system will have rank n minus 1. Why? Because it's a connected network. Okay, so to establish this result, so let's call n the number of zero eigenvalues in the Laplacian matrix, and let's call r the number of connected components in the graph. First thing we want to show is that the number of zero eigenvalues is at least as much as the number of connected components in the graph. So one thing to observe is that the vector of all ones is an eigenvector of the Laplacian. And to see that, note that the LF vector is, we just showed earlier, this sum here. So if all the FI's and FJ's are 1, this vector is 0, so therefore it has a 0 eigenvalue. Now that said, let's now think of a graph which is disconnected. I can play this same argument, use this exact same argument to argue that the vector of ones only corresponding to the nodes of the disconnected components is also an eigenvector with 0 eigenvalue. So if these are the two components of the graph and I take this vector, this is also a vector with 0 eigenvalue. Because this LFI can also apply to any disconnected component of this graph. So another eigenvalue of this specific another eigenvector of this specific graph with an eigenvalue of 0 is this one, corresponding to the disconnected part to the left. And I know that these two vectors, these two eigenvectors, are orthogonal to each other because their support is over mutually exclusive entries. So I know that these two vectors are linearly independent. So I have a trick now. You tell me what the disconnected components of the graph are. I can come up with eigenvalues of eigenvectors of that correspond to an eigenvalue of 0. This is the trick to do it. I know they are linearly independent, so I know that the number of eigenvalues, the number of times that the eigenvalue 0 occurs is at least as much as the number of disconnected components in the graph, just because I can play this trick over and over when you present me any disconnected graph. Now, so I've shown that this m, the number of the multiplicity of eigenvalue 0, is at least as much as the number of disconnected components of the graph. Let's prove the inequality in the other direction. So what we want to show now is that the multiplicity of eigenvalue 0 is no more than the number of disconnected components of the graph. Well, we can show that by showing that you tell me an eigenvector that has an eigenvalue of 0. I will show you that it is a linear combination of these eigenvectors that correspond to an eigenvalue of 0. And if I do that, I know that the inequality here holds. So I walk up to you, I present to you an eigenvector with an eigenvalue of 0. One thing that we established earlier is that this inner product is exactly this sum for any vector, including the specific candidate eigenvector with eigenvalue of 0 that I present to you. Well, now I know that this specific eigenvector v is an eigenvector with eigenvalue of 0, so I know that LV is 0. So I know that this sum here is 0. And the only way for that to happen is that the candidate vector that you present to me has Vi equal to Vj whenever there is an edge between I and j. Any candidate vector you present to me that has an eigenvalue of 0 has to have that property. So for example, it could be a vector like this. But it needs to satisfy this structure that if there is edges between these three components, the entries corresponding to these three entries have to be equal, otherwise the sum here could not be 0. The entries corresponding to the other disconnected part of the graph could be different, but between them they have to be equal, otherwise again the sum could not be 0. Well, if I'm constrained to present to you a candidate eigenvector with eigenvalue of 0 that always looks like this, then you can always come back to me and say, well, this is just a linear combination of 2 times this eigenvector plus 3 times this eigenvector. So I've just shown to you that any candidate eigenvector with eigenvalue of 0 that you present to me, I can express it as a linear combination of these original eigenvectors with eigenvalue of 0 that I came up with in the first part of the proof. And that establishes why m cannot be greater than r. So, bottom line, important takeaway here is if I have a connected graph, I know that its Laplacian has rank n minus 1, where n is the number of nodes. And we will use that in the next hour. Are there any questions? We can take a break. Okay, one warning about this coming hour is that there will be a lot of electrical engineering stuff. You will hear it once, and I'll give you the punchline, the bottom line of the analysis, and then you can just, focus on the analysis and kind of put the power engineering details on the side, but it just helps to give the mathematical background of what's going to happen. So we're going to do a bit of circuit theory for the next hour, and then arrive to the power flow equations that look like that use the Laplacian of a graph, and then we just establish that the rank of the equality constraints that associate the power flows over lines and the power injections over buses is n minus 1. So that's the whole goal of this presentation, is to arrive at that result and see the implications of that as far as trading is concerned. Okay, so the preview is that we're going to cover a bit of introductory circuit theory, use it to arrive to the power flow equations, linearize these equations to get 2 versions of the optimal power flow relationships. So a brief intro into circuits. When we're looking at electric power systems, there are 2 types of elements. We have loads that are we have active elements that in the language of circuit theory obey Ohm's law. So you apply a voltage across their terminals, we know what the current that goes through them will be as a consequence of Ohm's law. And there are other elements in the circuit. An example of a passive element is, for example, a coil. We know how a coil will behave if we apply a voltage across its terminals, or a resistor. An example of an active element, which does not follow Ohm's law, is an element that controls the voltage and the current. The voltage across its terminals and the current that flows through it. And such examples include, in the power systems that we will be seeing, generators and certain loads. So when we look at a generator as part of a circuit, the generator controls the voltage that across its terminals, the current that flows out of it, and therefore it controls how much power it produces. So that's the distinction to remember. So what does Ohm's law say for a passive electric element? it says that if I apply a voltage across its terminals, the amount of current that will flow through the passive element is equal to Y times V, where Y is called the admittance of this element, and it's just something that depends on the physical properties of the element. For a wire, for example, it's just its resistance, and the resistance depends on how thick the wire is or how long the wire is. But the bottom line is that for each passive element in a circuit, we can associate with it an admittance, and Ohm's law tells us if I apply this much voltage, this is how much current will go through the element. Then the power that's consumed within this element is given by this relationship here that multiplies the voltage across the terminals times the conjugate of the current. You see here a conjugate notation because voltage and current are represented as complex numbers. We will see why that's the case. It has to do with the fact that in AC circuits there's a sinusoidal fluctuation of voltage and current, and the best way to represent that is using complex numbers. It makes computation very easy, very automated, and very fast. Yeah, this S, this product of voltage and conjugate of current is what is called the apparent power that flows through the element. What we are used to as power, what we understand as power, so the useful energy that comes out of electricity is just the real part of this product here, and it's called the real power. This is the one that we will focus in the power flow equations. Okay, so to arrive to the power flow equations, and just to give, before starting to get too technical, I want to give you a bit of a context of why we're even doing all of this. When we're trading goods in normal networks, like for example in a highway, we get to decide. If I sell a truck of tomatoes to someone in Charleroi, I send a truck from my shop in Brussels to Charleroi. I decide the routes that the truck takes to get to Charleroi. It's up to me how to route my product through the transportation network. In electric power systems, it's not that simple. If I am a generator located in Charleroi and I want to sell power to a load in Brussels, there will be a transmission line that can carry power from Charleroi to Brussels. The problem is that there are also other transmission lines throughout the Belgian network as well as throughout the European network. And when I decide I will send you 5 megawatts because the auction cleared and I decide that I sell to you these 5 megawatts, as I'm sending power over this line, there will be other flows of power through the rest of the lines of the network as a consequence of the physics that we will see now. So if I want to send 5 megawatts from generator location to the load location, I don't decide the path that the electricity takes. Therefore, and the problem is this: if these lines never get congested, if they're never under physical pressure, that's okay. I mean, I can send as much as I want and we can take care of exchanging power together. But there are limits over how much power can flow over these lines. So if we send too much, we can end up burning the line. And that creates constraints between regarding how much power we can ship from one location to another. So we have constraints on how much power can flow over these lines, and also we don't get to control how the power is routed over the network. And understanding the physics of what happens if I ship power from here to here is the whole goal of this lecture, because what we're going to see later is that we then need to organize a new product in this market, a product for transmission rights over these lines that are traded using, in fact, the power flow equation. So the way these, the prices for these products are traded need to account for the power flow equations. So this is the motivation of everything that you're going to see today. Okay, so that said, the notation we will be using is the following. We will have this is a general representation of an N-port network. You can represent any circuit like this. The connections between nodes within the box are all passive elements, and anything that is to the left are active elements. So, for example, if we had a generator that is just passing power through a resistor, and the representation in terms of what you're seeing there is we create a bus here called bus 1 for one edge of the resistor. We create a bus 0 for the ground. This is a power engineering notation of ground. And the active element has one of its sides connected to the ground, so it's connected to port 0, and it's injecting power into this resistor. So that's, and then if you have more of these nodes running from one to n, you can imagine that anything I can come up with here, as complex as it may be, can be represented through this setup here. So the power that, the current that runs from active element 1 into the rest of the circuit is denoted I1. The voltage along between active element 1 and ground is denoted V1. Generally it's VM and IM, and the apparent power that is injected from this generator into the network is VA, the voltage across its terminals, times the conjugate of the current that it throws into the network. And important to remember that everything needs to be, all the active elements need to be connected on their other side to ground. So all the generators that are in the network have their other side connected to ground. And now what we will be looking at is systems with alternating current, just because 99% of the circuits that carry electricity to our homes run on alternating current. This is very different from what you have in, like, this pointer, for example, where we have a battery, a DC battery, and it's sending constant current with a constant voltage through all the circuitry in the pointer. And our lights here, for example, have a voltage across our terminals that is fluctuating with the frequency of 50 Hz. So every 20 milliseconds, the voltage along the terminals of these lights peaks, and then peaks in the positive value, and then in a negative value, and this happens 50 times every second. So does the current that is running through the filaments of the lights. The frequency is slightly higher in the United States, but the bottom line is that this influences the math that we use to describe the electricity, voltage, and power consumption along these elements. So the way to think of what's going on is by representing the voltage as a rotating vector. If I have a vector that is rotating around 50 times per second, and I take the projection of this vector in the x-axis, and assuming this vector rotates at constant angular frequency, this projection over here is something that over time fluctuates sinusoidally. Why? Because the projection of this vector on the x-axis is just a cosine of the magnitude of the vector, and if this thing is shifting with a constant angular velocity, it's cosine of omega t, where omega is the angular velocity of the vector. So the voltage across the terminals of a passive element, we can describe it as a vector that is rotating with constant frequency, and we will refer to the amplitude as the peak of the signal. So this could be the voltage, for example, across the terminals of this lamp over here. The amplitude is this, the peak of the signal, and the phase angle here is the time difference. The time difference between the start of the signal and our reference time, which is 0. And you can get this signal over time just by thinking of it as a vector that's running over the circle and taking the horizontal projection. Now, maybe instead of this slide, I'll jump you straight to the next example. But the one thing I want to point out is just the definitions here. So I referred earlier to Ohm's law, and I said that each passive element has this Y characteristic that from Ohm's law tells us what happens if I apply this sinusoidal voltage across its terminals. The Ohm's law tells us that the current I get is Y times V, and we will see what this means through an example. So suppose we have a lamp which is an inductive element, and this Y is called the admittance of the element, and it's a complex number. We'll see why representing it as a complex number helps, and its real part is called conductance, and the part we will focus on, which is the imaginary part, is called the susceptance. And here we have an example of a lamp. So its conductance is the real part, its susceptance is minus 0.01. And suppose we apply a voltage of 230 volts. Applying a voltage of 230 volts across this lamp in alternating current language doesn't mean a constant voltage of 230 volts. It means a signal that peaks at 230 volts and has a each period of the signal is 20 milliseconds. So in 1 second, this thing does this fluctuation 50 times. That's what is meant here by 230 volts, because now we're thinking of alternating current. What Ohm's law tells us is that the current that will flow through this lamp is given by voltage times the admittance, which is this complex number here. So how to interpret this complex number? This is also a sinusoidal signal. Its magnitude is the peak of the signal, so 3.25 is the magnitude of this complex vector. So if we're working in a complex plane, 2.3 plus 2.3i is this thing here. So the magnitude of this is the peak of the sinusoidal signal, and the phase is the angle with respect to the real axis. So for this particular signal, the imaginary part is negative, so in fact the phase is negative, which translates into the fact that the current running through the signal has a delay with respect to the voltage. So this is just a brief illustration of the fact that we can use complex arithmetic to represent signals that are evolving sinusoidally over time. It's a very economic way to do the math when you're working with sinusoidal signals. You just replace everything by complex numbers, and all the algebra falls through. So that's what I wanted to say about the complex arithmetic. Now, a couple more definitions. So, when we are applying a, well, actually I covered this earlier. So when we're applying a voltage Mn across terminals of an element, the product of that and the conjugate of the power is the apparent power, the real part is the real power that we care about, and there is another component called the reactive power. So that's a bunch of definitions there. Now moving to the power flow equations, again, what we are interested in the n-port network that we saw earlier is how power routes through each of these connectors, because these are the ones that create constraints for trading. So to come up and what we really want to come up with is a relationship that tells us what happens when I inject 5 megawatts here, 10 megawatts here. What happens? How many megawatts will flow through this element, and so on. So what we want to create is a mapping from injections to flow over lines. This is the relationship we want to establish. So to do that, we need to use two laws from Kirchhoff. So one law says that in a circuit, when you can't have storage of current cannot accumulate in any part of the circuit. Any current that comes in to a certain part of the circuit has to run out of that part of the circuit. And the other law of Kirchhoff is the voltage law. That's kind of like a statement of the conservation of energy that says that what goes up must go down. So if this battery is increasing voltage by 10 volts, then the voltage drop across this resistor has to be 10 volts, because if I do a full circuit of this, if I do a full tour of the circuit, the sum of the voltages has to sum up to 0. This is kind of like a law of conservation of energy for electric circuits. So, using these two laws of Kirchhoff, we can write a bunch of equations here, linear relationships between the voltages we apply across the terminals of our network and the current that's flowing through all of these lines. That's very powerful. You tell me what the voltages are at the ends of the active elements. I tell you how much current will flow through each of these elements, and that's getting us much closer now to what we want to get to, which is how much power will be consumed, will be routed through each of these elements. So what we, the way we arrive at power quantities is the following. So if you remember earlier, over here, if we look at bus 1 and we apply Kirchhoff's law, we know that what comes into bus 1 it has to equal what goes out from bus 1 to all of the other buses, and that's just stated through this equality constraint here. And now what we care about, again, we're focusing on power, is how much power is injected from that active element into the network, and that's just the voltage times current conjugate, which, using the Kirchhoff current law, is this quantity over here. If you do a bunch of, and then what we're specifically interested in is the real component of this. So that's the what we understand as real power injected into the network from that bus, which is given over here. And if we do the complex algebra, then we keep, so remember, y is g plus ib, and we have the voltages of Vn conjugate is just this quantity here, where theta min is the angle of voltage at m minus the angle at n. So if we do all the complex algebra, the real part of this thing here is just given by this equality constraint here. So now we found a way to associate the power that's injected at a certain port to the angular differences between voltages along these lines. So this equation here is telling me, you tell me what the phase angle differences are for the voltages along each bus of the network. I can tell you how much power is injected from each generator in the network. And this is now something that will directly show up in our power flow models. So these relationships, we will linearize them and they will come up as equality constraints in the canonical dispatch problem. Okay, and we do three, we take these, this nonlinear relationship here and we do three approximations. First of all, we ignore the resistance across the elements of the circuit. So that is effectively saying that whatever losses occur along the lines, we forget about them. We approximate the theta mn by something, for power systems to run in a stable way, the angle differences along voltages of different buses have to be very small. Otherwise, we have instabilities and blackouts. So the theta mn we know is going to be something very small. So the Taylor approximation of the sine is just the theta mn, and the Taylor approximation of the cosine is 1. And we also know that in stable operations of power systems, the voltages at the buses are approximately equal to 1 per unit. So if we do these three simplifications here, which are listed over here, we get a very simple relationship. We're just left with the power injected at a location M is just this sum over here. So we see that the power injected in location N depends on the bus angle differences among different buses. And then I'm just substituting the BMN with the reactance of the line, which is the way lines are described in physical circuits. I will use this reactance in the examples. We won't be using the B in the examples that you will see. We'll be using the reactance of the line, which is just the inverse of the B. So we're left with this set of linear equalities here. So we're making some progress. We now have a set of linear equalities that establishes a relationship between bus angles in different buses and the power that's injected into the network. And this is where all this discussion about the Laplacians comes into the picture. So if you look at these relationships here, with some manipulation, you will see that basically we can write that compactly as the linear system over here, where P is the power injected in a bus. It's the vector of powers injected in the bus, with the exception of one bus which we will call that the hub node, which has an angle that we fix to 0. And we have this linear system here. So power injected into a bus is equal to this T matrix times the bus angle. Now the T matrix looks a lot like the Laplacian of the network, but it's not exactly the Laplacian, it's a weighted Laplacian. So if we had minus 1s here and 1s here, this would have been exactly the Laplacian of the network. So this is important because it says that it establishes the fact that the T matrix is invertible. So I should be more accurate here to say that if we had this bunch of equality constraints, including the hub node, that would be the weighted Laplacian of the network. what we've done is we've taken this rank n-1 system, taken away the rows associated with the hub node, taken away the columns associated with the hub node. So we've removed from a rank n-1 matrix one row and one column. We're left with a matrix that is invertible. And the punchline, the bottom line that is important to remember is that since this matrix T is invertible, there's a one-to-one relationship between power injections and bus angles. And this is the set of equality constraints that we will throw into the economic dispatch problem to convert it to the optimal power flow problem. This is really all the takeaway of the physics you've seen so far. The whole goal was to lead us up to this point of establishing this one-to-one relationship. You want to tell me how much power you're injecting in the network or what the bus angles are in the network? It's the same thing. I can jump from one to the other. Okay, and that's just a lot of decorative language to describe that. So the goal of the last bullet is to show you an alternative way to represent the power flow equations, where what we saw so far is a relationship between power injections and voltage angles. Now what I want to establish is a relationship between power injections and flows of power along the line, which is another way to represent these constraints. They're not the same thing and they're useful for different models, but they are both equivalent ways of describing all the circuitry in the electricity network. So the way we establish this relationship between power injections and the flow of power over lines is through this equality constraint here. Again, it comes out of the physics of the network, and we won't go through it in detail, but it's saying that the amount of power that flows in any given line is the difference of the bus angle in the from node and the to node. So you want to tell me what the bus angles are over all the nodes of this network? I can tell you how much power is flowing over these lines. And in fact, if the bus angle in the from line is higher than the to line, I know that the power is flowing in this direction. So we use this to create a mapping now. Since we have a way to jump from power production to bus angles, and we have a way to jump from bus angles to power flow, we just created direct mapping from power production to power flow. And what we get is these constants that create this mapping that are called the power transfer distribution factors. And they're just basically plugging these equations into these linear equality constraints here in the way that we will immediately see. So we have, if you look at the way we define this matrix, capital M, PL here represents the flow of power over the lines. This matrix M is just reiterating this bunch of qualities over here. So I'm looking at my network. If there is a link, if there is a link, so to create this matrix M, first of all, it has it's defined over L as the row, as the set of rows, and N minus hub as the set of columns. And for entry Kn, I look at my actual physical network, nth bus, line K, if there is a line that originates from N and points into any other bus N that is not the hub, and if the reactance of this line is xk, I put an entry here of 1 over xk. If this were the other way around, so these are directed lines, if this were the other way around, so in that case this would have been minus 1 over xk. So the way we're constructing this matrix is just by observing these equality constraints over here. And then if there is no link between these two in the physical network, the entry here of n becomes 0. So just by staring at a network, if I tell you what the xk's are, you can easily construct this matrix. Okay, so what we know is that P equals theta. This is one mapping that gives us a one-to-one correspondence between power injections and angles. We also have PL equals M theta. That gives us a mapping from the bus angles to the flow of power. So what we can do now is basically to establish a relationship between these two guys, I just inverted this relationship here. So what I get is theta equals T inverse P, and plug it into here. And this is really what we want. We want a way to map power injection in a certain location to power flow over a line. This is the map. This is the mapping that we were going after. And there's a very natural interpretation of these linear relationships. They're saying that when I'm shipping power from, for example, Charleroi to Brussels, the way to analyze what I did in this part of the circuit over here is one of these nodes is the hub node, for example, this node here. By defining that hub node, we can use all the expressions in, which you have for creating a matrix T. We can also look at the graph and create a matrix N. And now there is a constant that tells me that whenever I ship power from Charleroi to Brussels, that's equivalent to shipping power from Charleroi to the hub and from the hub to Brussels. But these equality constraints tell me what's going to happen in each of these lines if I ship power from Charleroi to the hub. There's this number here coming out of this matrix that tells me that whenever I do that, some power will flow over here. And whenever I ship power from the hub to Brussels, some power, a bit of it will flow in the opposite direction, but the sum of the two is basically going to give me the amount of power that flows when I ship electricity from Charleroi to Brussels. So the important thing, the takeaway is that these relationships are linear, and we will see a consequence of that in these two examples here. The fact that I've established that these relationships between flows over lines and injections in buses are linear, first of all, it implies proportionality. So if I have this network here where I'm producing 100 at bus 3, and I'm going to consume it at bus 2, I can get, if you told me the physical characteristics of this network, I could derive from all this math how these flows are going to split over these lines. But suppose you immediately told me, I know that in this network, if I ship 100, if I produce 103 and consume it in 2, I tell you already that I know that the flows will go as follows. A third of the power will go from 3 to 1 to 2, and 2/3 of the power will go from 3 to 2. You know then what's going to happen if you produce triple the quantity over here, because these are the relationship between power flows and injections is linear. So if I produce triple the quantity here and consume triple the quantity in bus 2, I also know that the flows over the lines will be triple. But that's not the only thing I know. I know that I can also add up flows. So if I have 2 trades here, in one trade I am producing at location 3 and consuming at location 2, and I know that this trade is causing these flows of powers over lines. And in another trade, I'm producing at location 150 and consuming it at location 2, and I know that that trade is causing these flows over here. Then I know that by summing up these 2 trades, also the flows over the lines will sum up. So when I'm jointly producing 100 here and 50 here, and I'm consuming 150 in location 2, I know that the consequences on line 1,3 will be the sum of 33 in the down direction and 17 in the up direction. Is that clear? That's very important for trading purposes because you can create financial instruments out of this. Okay. So these 2 properties are very important to see. Is it clear? The linearity?
Yeah, but I don't understand why in the third graph it's 17 between 1 and 3.
Rounded. Oh.
Yeah, it's 16.
Yeah, no, it's. I mean, if you actually take the numbers, because this is a symmetric network, it's actually 16.6667. I'm just rounding here, but you're right. Actually, we're going to derive these flows for a symmetric network from first principles in this example. Here. Okay. So. Yeah, here's an example of how you create the. So here's an example of how you derive. Here I told you what the flows were. Here's an example of how you derive the flows from first principles. So I know for this network that the x's, those are the reactances. If you remember earlier in the slide, the xk's are given for each of these lines by this number. And I also know the injection of power is 0.2 over here, 0.5 over here, and 0.25 in node 3. So now we're asked to actually come up with what the power flows are going to be over these lines. If you look back to all the physics we went through, the way to do that is to first construct the capital T matrix. To construct the capital T matrix, what you do is you go node by node, starting from node 1. You look at what nodes this node is connected to, and you take the inverse of the reactances and sum them up. So I know 1 is connected to 2, the reactance is 1. I know 1 is connected to 0, the reactance is 1.5. So that's how this element is coming up here. And then minus this shows up in entry 2 because node 1 is connected to node 2. This corresponds to node 3, this column, and node 1 is not connected to node 3, so the entry here is 0. And the same logic applies for constructing the rest of the matrix. So for example, if you go to node 2, you see that it's connected to 3 other nodes, 1, 0, and 3. And you're just taking 1 over the reactance of these 3 guys to come up with the diagonal element. Here you can already see how this looks like a weighted Laplacian. And basically, you're asked in the exercise to show that T is invertible. If I just asked you by staring at it, it does have this specific structure that looks a lot like a Laplacian, but by going through the analysis thoroughly from the slide deck that we went through earlier, it immediately drops off as a consequence of the background I covered earlier. Okay, so we're looking good. We have the T matrix for this network. This is the matrix that tells us the relationship between bus angles and power production. So we invert that, and since we know the power injections, so in bus 1 we're injecting 0.2, in bus 2 we're injecting 0.5, and in bus 3 we're consuming 0.25, we can get the bus angles by the T inverse P relationship. So it turns out that for these injections, these are the bus angles we get, and then the power flows are just the bus angle differences divided by the reactances. So you see a specific example where I give you the power injections, I give you the electrical characteristics of the lines, you give me the flows. Important thing to note, when one bus has a higher angle, for example here, than another bus, power flows from bus 1 to bus 0 and the other way around, because the x's are always positive. And then we can also compute the power transfer distribution factor, which is basically the constant that's linking injection at a certain bus to flow over a certain line. We just formed the M matrix, again according to the equations that are in the notes, and the power transfer distribution factor of line 2, 3 for bus 1 is this number here. Now, this is just the mechanics of computing it, which you can do. The important thing is to understand what it means. Power transfer distribution factor from a bus to a line is the amount of power that will flow over that line when I'm sending a unit of power from bus 1 to the hub. The hub in the specific example was chosen to be 0. So when I'm sending a unit of power from 1 to 0, and I want to look at the impact on line 2, 3, some of the power will be routed from 1 to 2 and down. Some of it will then not go directly down, but will go 2 to 3 and from 3 to 0. So a certain fraction of this unit power that I'm sending to 0 is the PTDF, the power transfer distribution factor over line 2, 3, and it's given by this number here. So 12% of the power I ship, from 1 to 0, 12% of that will flow through line 2, 3, and you can immediately get it from these equations here. The last example I wanted to show you, which gives you a lot of intuition behind the physics, is a symmetric 3-node network. And the goal here is to derive the PTDFs of this network. And again, if you go through all this algebra of forming the T matrix and then inverting it, the important thing, however, to note is that by symmetric, I mean that the reactances are the same for all of these 3 lines. So these 3 lines are identical, basically. And we're assuming that 3 is the hub node here. So when we form the PTDFs, we get these results over here, and I will quickly decode them for you. The intuition for understanding PTDFs is that current will always choose the easiest path to a destination. So let's look at the PTDF from bus 1 over line 1, 2. This is basically asking, when I'm sending 1 unit of power from 1 to the hub, which is 3, how much of it will flow through line 1, 2? what do you think is easier for the electricity to go? Go through directly to 1,3 or take this path over here? Direct, right. So the way electricity splits itself is if this long path is 2 times harder, and 2 times less current will flow through. So 1/3 of the power will go through the easy path. 2/3 of the power will go through the fast path. 1/3 will go through the easy path. That's all the PTDFs are saying here. So if you read through these numbers, the PTDF over line 2 is 1/3. Over the short path, it's 2/3. And we get these PTDFs for each of the 2 buses with respect to the hub, which we have defined as bus 3. And with that, I think that we went through the painful part of the physics of the course. It's the takeaway to remember is the PTDFs and the linear relationship between injections and flows on lines.